Hello again. In this segment of the notes, we will cover Section 2 and begin Section 3. We will finish Section 3 problems in class together. What can we measure? Although there are 7 basic physical quantities to measure, we will only work with about 5 of them this year. Length, which is measured in meters, mass, which is measured in kilograms, time, measured in seconds, temperature, which we will use the Kelvin scale for, and the amount of substance, which is the mole. We'll talk more about the mole later this year as well. All other measurements will be derived from these basic units, things such as velocity, which is a length divided by a time unit, so it has units of meters per second. Acceleration is another example where you take velocity and divide it again by time, so it has meters per second as its units, or another way to write that is meters per second squared. In 1960, an international committee agreed on a system of standard units for measurement. This is known as the International System for Units. When measuring, it's important that you have good measuring devices. So every measuring device in the world is calibrated to give consistent results. Not all units are base units, such as meters for length, seconds for time, etc. Some are derived units, like those that we saw for velocity and acceleration. They're formed by combining 2 or more of the basic units using multiplication or division. There are 2 basic ways to work with extremely large or extremely small numbers. Using scientific notation, where something is taken times 10 to a power, where the number is somewhere between 1 and 10 but can't be 10, and of course that exponent n indicates how far to the left or to the right to move the decimal point. Or another choice is to use prefixes, such as milli or micro for small measurements, and kilo or mega for larger measurements. You should be familiar with or comfortable switching between the metric prefixes found in this table. Pause the video for just a moment and look these over so you feel comfortable with the way it's set up. It goes from very large units, mega, with a capital M, down through very small units, pico, with a lowercase p. This table shows how big certain length units are. You should pause the video to look these over so that you kind of have a feel for how big each one of these units actually is. We can also measure volume. Now, volume is the space occupied by an object. Since space is 3-dimensional, it involves multiplying 3 length units. In SI units, which is what we call the International System of Units, the standard unit is cubic meters. If an object is irregular, its volume is usually found by water displacement rather than by using a formula. We don't have formulas for irregularly shaped objects. The non-SI unit commonly used for liquid volume is the liter. You can convert from this non-SI unit into an SI unit for volume by understanding that 1 cubic meter is equivalent to 1,000 liters, and 1 liter is equal to 1,000 cubic centimeters if you're dealing with a very small quantity. Take a moment to look over this table. It shows how big certain volume units are. Pause the video and take a look. Please note that this is a very important conversion between solid volume units, cubic centimeters, and liquid volume units, milliliters. So you want to remember this one. When you measure liquid volume, it can be measured using equipment such as measuring cups, beakers, graduated cylinders, pipettes, volumetric flasks, and syringes. There are other devices as well, but this gives you a nice sampling of them. Which one you use is going to depend upon the precision needed in the measurement. As mentioned in Chapter 2, mass is a measure of the amount of matter in an object, usually measured in kilograms, grams, milligrams, or even micrograms, depending upon how massive the object is. This value does not depend upon the location of the object. Mass is a measure of how much matter the object contains. It is not based upon gravity of a particular location. Mass is measured using a balance. This is a mass balance where you place an object on the pan, as you see the weight has been placed there, and then you move slider masses until you have a balance between the masses on the sliders and the mass that you have on the pan. Weight is a measure of the gravitational force exerted on an object. So its location on a particular planet, moon, or even out in deep space can and will affect the object's weight. Weight is measured using a different device. It's measured using a spring scale. You can see a couple of different spring scale designs shown to the right. You may have seen ones like the one on the far right at the local grocery store in the produce department. Of course, there wasn't a baby in it. There was just an empty metal pan for you to place your produce in so that you can measure out your weight of potatoes or bananas or things like that. Objects may become weightless, but they cannot become massless. Remember, weight depends upon gravitational attraction in your location. Mass does not. When measuring temperature, we have a variety of temperature scales that we can use. We all know that the temperature is a measure of how hot or cold something is. We're used to using the Fahrenheit scale shown on the far left, but that scale really isn't used much in science. A few engineers may use it, but most scientists use the International System units, which are Celsius and Kelvin is the best because it doesn't include negative numbers. You can switch back and forth between the Kelvin and the Celsius scale by adding or subtracting 273. That's because the Kelvin scale was created in order to get rid of negative values for your temperature. So the 0 point on the Celsius scale is at the freezing point of water. In the Kelvin scale, they have moved that 0 point down to the absolute lowest temperature possible, and they called that absolute zero. Therefore, there will never be negative numbers in the Kelvin scale. So although you may be used to the Fahrenheit scale, in chemistry we use Kelvin or Celsius. Let's try a problem. The boiling point of water on top of Mount Everest is 343 Kelvin. Notice I didn't say degrees Kelvin because we don't use the degree symbol in the Kelvin scale. At the bottom of Death Valley in California, water boils at 373.3 Kelvin. Express these in degrees Celsius. So we have the Kelvin temperature. We want to find the Celsius temperature. It really doesn't matter which one of those formulas you use. However, the one on the bottom is already solved for degrees Celsius, so it's probably the easiest to use. We would substitute 273.3 in for K in that bottom equation and subtract 273. When we do that, we get 100.3. But be careful, remember significant figures. When we add or we subtract, we look at our leftmost uncertain digit. That 273, we only know to the ones place, so we would need to round this answer to the ones place. We would report this as 100 degrees Celsius, and it would be a good idea to put a decimal at the end of 100 to indicate that our answer is actually known down to the nearest degree Celsius. We will work this problem in class. Now, what's the difference? The size of a Kelvin is the same as a degree Celsius. That hasn't changed. The Kelvin scale does not have negative numbers because, as I said, 0 is set at the lowest temperature possible, absolute 0. And that is, to more precision than what we were working with in those formulas, about negative 273.15 on the Celsius scale. The coldest temperature achieved so far in a laboratory is only half of a nanokelvin above absolute 0. The cold temperature of outer space is actually 2.7 Kelvin, not 0. When you make a snowball with bare hands, your hands become cold like the snow. Do your hands absorb cold from the snow? Actually, heat moves from hotter objects to cooler objects, not the other way around. As objects heat up, they usually expand. Now, that's not always the case, but they usually do. So you can see on the left, at low temperatures, the particles move less, and of course, they take up less space. They can compact closer together for most substances. On the right, we can see that at high temperatures, particles are moving more and more, which allows them to move further from their neighbors, and they take up more space. So the object that's made up of this matter expands. Heat transfer involves energy. Energy is defined as the capacity to do work or to produce heat. When heat is transferred, a transfer of energy has taken place. Energy is commonly measured in joules, abbreviated capital J, which is the standard unit for energy, or it may be measured in calories, which is abbreviated CAL. Now this calorie is different than the one in your diet. You may notice that they usually capitalize the word calorie when they're talking about calories in your diet. And that's to differentiate it from the chemistry term calorie, because a calorie with a capital C from your diet is actually 1,000 calories from chemistry, or another way of saying it is it's 1 kilocalorie. A calorie is larger than a joule. 1 calorie equals 4.184 joules, or you can also remember it as 1 joule is only 0.2390 of a calorie. Now we're going to talk about conversion factors. They become very important during certain chapters of this year. Conversion factors are just FFUs, which is another way of saying a fancy form of the number 1. These can be created from any equivalent relationship. If we were converting between energy units, our conversion factor is formed by creating a ratio, and of course that ratio is equal to 1, from the fact that 1 calorie is equal to 4.184 joules. So I could write that ratio in either of these forms that you see at the bottom of the screen. Given that 1 meter is the same as 100 centimeters, which is the same as 1 times 10 to the 6th micrometers, if we want to change between centimeters and micrometers, we can set up 2 different conversion factors depending upon which direction we need to change it. We would want the units to cancel. Setting up problems so that the units will work out correctly is using dimensional analysis. Conversion factors allow you to change from one unit to another in a problem. If you want to change from centimeters to micrometers, you would use 1 times 10 to the 6th micrometers over 100 centimeters to get the centimeters to cancel. 23 centimeters changing into micrometers. By setting the fraction up this way, we can see that the centimeters will cancel, and we multiply by 1 times 10 to the 6th and divide by 100. We find that we get 2.3 times 10 to the 4th micrometers is equivalent to 23 centimeters. Take a moment to try and work through these problems, and then we will discuss them further in class. An experiment requires that each student use an 8.5 centimeter length of magnesium ribbon. How many students can do the experiment if there is a 570 centimeter length of magnesium available? First, let's make sure you understand the given information. Each student needs 8.5 centimeters. So we know that there's 8.5 centimeters per one student. The amount that we have is 570 centimeters. Our conversion factor should be obvious here because it's a ratio. How do we set up the problem so our final unit is students? We can't multiply them the way they're written right now because student is on the bottom and centimeters on the top. So centimeters would not cancel, and we'd have per student, not students, as our unit. We'd end up with centimeters squared per student. So instead of setting it up that way, the way it's written, we can take that ratio and flip it over and use it as a conversion factor in its flipped over form. 570 centimeters times one student per 8.5 centimeters will allow centimeters to cancel and give us units of students. We will be working through some other problems together in class. You can try them for yourself if you like, but please, if you do try them, don't try to do them just any way you want. Please practice using the conversion factors to solve these problems. They are going to be essential when we get into second semester material. One last thing that I want to mention before signing off for today is why would we use dimensional analysis? Dimensional analysis is a powerful problem-solving tool. It's extremely helpful when multiple conversion factors need to be used to work out a problem. Properly manipulating the units assures accurate manipulation of the numbers as well. This problem-solving technique, as I said, will be essential this year when we get to second semester especially. Now, the remainder of the problems we will be working together in class. As I said, you can try them if you'd like, and then I'll go through them in class. And I hope that this set of notes has been helpful to you. I know that a lot of students fight using conversion factors and dimensional analysis, but it can be a really powerful tool if you give it a chance.